Hello. Today we're going to learn to classify chemical reactions. And the way we'll do this is just generally look to see what is being combined. So let me go through some of these examples and we'll practice this. The first type of chemical equation that I want to talk about is called synthesis. And when you see the word synthesis, hopefully you think about combining things. You might think about photosynthesis, okay? And generically, we're going to say this is A plus B goes to AB. So things get put together. Okay. I'll go to an example here real quick, maybe. All right, so here's some synthesis reactions. The leaf reminds us of photosynthesis. And of course, here it's carbon dioxide plus water makes sugar. And then of course there's oxygen. So that doesn't really look like A plus B goes to AB, but it just reminds you of parts being brought to a whole. Of course, we could balance that if it makes you feel better. That's not what this lesson is about. The next one, let's talk about the formation of water. Water is formed from gases hydrogen and oxygen combining to form H2O. Now, I'm going to go ahead and balance that chemical equation by adding a coefficient 2 in front of both of the hydrogens. Now, hopefully, when you look at that, if you wear glasses, take your glasses off so it's kind of blurry. And what it should look like is sort of A plus B goes to AB. That's what I mean when I say you can just look at it and figure out what this is. Let's try another one, the formation of salt. So for salt, you take sodium metal and chlorine gas, and you'll make NaCl. We'll go ahead and balance that with the coefficients of 2 in front of each of the sodiums. And again, I hope when you look at that, just from first blush, it looks like A plus B goes to AB. That's what all synthesis reactions would look like. A plus B goes to, and I don't want to call it C, I'd prefer to call that AB. Now, I could have A plus B plus C goes to ABC. There's lots of ways you can combine things, but those are all synthesis. All right, if you can put things together, synthesis, you can break them apart. That would be decomposition. So if we just reverse the reaction, AB goes to A plus B, we're talking about a decomposition reaction. So let me go through some examples of that for you here. Hydrogen peroxide, that's the stuff in a brown bottle. You would have it, you'd pour it on a cut to clean out the wound, and it would rinse away any debris inside your body as well as add oxygen to help the healing a little bit. Well, hydrogen peroxide has the formula H2O2, and when you shine sunlight on it, it breaks into water and oxygen gas. We'll go ahead and balance this. Notice that we have an even-odd situation. We have 2 oxygens on the reactant side, 1 here plus 2, 3, so we get an even-odd. So at minimum, we need to make this one even. So by adding a coefficient of 2 in front of each of the hydrogens, that balances the equation for us. And again, if you're looking at this just very, very quickly, it looks like AB goes to A plus B. One big thing breaks into parts. That's what a decomposition reaction will always look like. Here's another example, that electrolysis of water. This is where you use electricity to split water. So water, if you pass electric current through it, will decompose into hydrogen and oxygen gas. Now, if we balance that, notice that we have 2 oxygens on the product side, 1 on the reactant, so we need a coefficient of 2 and 2 in front of each hydrogen to make that balance. What it says is you'll get 2 parts hydrogen gas for every 1 part oxygen. So if you look very carefully here, this is how much we have of one gas, this is how much we have of the other gas. So the one that has 2 must be the hydrogen, the one that has 1 part is the oxygen. And that's what these coefficients are telling us. There's a 2-to-1 ratio. And again, I hope if you look at this, you see AB goes to A plus B. Last example I'll give you is nitrogen triiodide. This is a touch-sensitive explosive. It is the combination of nitrogen, iodide, and iodine together in this very unholy conformation, Ni3. It just doesn't want to be that way. And if you literally touch it with a feather, it will explode and return to nitrogen gas and iodine gas. Now, we do need to balance this one. I notice I have 2 nitrogens and 1 nitrogen here, so I need to put a coefficient 2 in front of the nitrogen. That now gives me 6 iodide. I have only 2, so I need a coefficient 3 here, and now that one is balanced. Again, we're not worried about balancing at this point. What we're trying to do is classify. So hopefully you see the general form of all 3 of these are AB goes to A plus B. That's what a decomposition will look like. All right, let's do this. Let's jump ahead a little bit and let's go right to here. Now, let's see if we can classify some of these. If you look at that first one, I hope that the way that looks to you is that's A plus B goes to AB. Well, that's a synthesis, isn't it? Okay. Look down this page. Can you find another one that's synthesis? Good. If you said number 2 is synthesis, you're correct. Okay. Let's look for a decomposition. Do you see any decomposition? Look at number 3. Isn't number 3 say AB goes to A plus B? It sure does. That's a decomposition. Can you find another decomposition on there for me? Well, if you said number 4, I would have to agree with you. That's also a decomposition. Let's go back to the list and learn about other ways, because you see we're trying to classify as synthesis, which we understand, decomposition, which we understand, and we've got a couple more, single and double replacement. So let's make sure we get to that next. So a single replacement reaction involves an element and a compound turning into an element and a compound. So what we're looking at here is an element A and a compound BC turning into a compound and an element. So in this case, A has to take the place of B. And when it does that, B gets kicked out as an element by itself. Now, in class, I'll give you a story about this, maybe to help you remember it. At this point, I just want you to recognize what you're looking for. An element and a compound turns into an element and a compound. Now, A could either replace B or C, but it will replace its similar type atom. What I mean by that is a metal, if A is a metal, then it will replace B, the metal. If A is a nonmetal, it will replace C, the nonmetal, in that compound or that salt. So let's look at this single replacement reaction. So in the first case, maybe you remember, and I'm not even sure if I did it this year, but we were talking about the 4-element theory where we had fire, air, earth, and water. And magic blue earth is actually a chemical. It is copper to chloride, and it's blue in color, and it comes from the earth, so I call it magic blue earth. And if you sprinkle iron filings in it, which are iron is black, what happens is the iron will replace the copper in solution, and what we're left with is simply iron chloride and copper. Now, I added this little thing on the side. It's called the activity series. It refers to chemical reactivity. Now, scientists have ran all these experiments. They know which ones are more reactive. If you're ranked higher up, you can replace things lower down. So I'm always looking, can the single element, in this case iron, right here, replace copper down here? And because iron is listed higher up, the answer is yes, it can replace it. And therefore, we're going to end up getting iron chloride plus copper. Okay? I'll demonstrate this chemical reaction at school for you so you can see it. Maybe I'll make a short video so you can see that particular chemical reaction taking place. Now, these reactions are one directional. If you were to reverse this, and simply write Cu plus FeCl2 and ask what will happen. Well, the question is, can the single element copper replace its counterpart iron? And the answer is no. Copper's listed lower down cannot. There will be no reaction for that. So it's only a one-way street. All right, let's try another example of a single replacement reaction. How about this? Zinc and nitric acid. So zinc is a metal and hydrogen's a nonmetal, but so is nitrate. Well, normally nitrate salts have metal nonmetals. So in this case, zinc is going to try to replace the hydrogen, the first thing. So I look on my activity series and I find zinc on there. Where's zinc? Let's see. Right here in the middle. Now, hydrogen is way down here. Can zinc replace hydrogen? The answer is yes, because it's higher up on the activity series. Okay, that's what the activity series tells me. So therefore, I'm going to get zinc nitrate plus hydrogen gas. I went ahead and balanced that equation. Please remember that hydrogen is always diatomic H2. Now, zinc, when it is an element, has no charge. But when it's an ion, it's a 2+ ion. Nitrate's a 1- ion. So when it does the crisscross, the formula for this is ZnNO3 2. Again, we can balance it. The key here is you're seeing an element, zinc, plus a compound, nitric acid, turns into an element, hydrogen, and a compound. That is what a single replacement reaction will always look like. Let's try this one. Now, magnesium chloride plus bromine. Now, you want to be careful. The question we have to ask is not, can chlorine replace bromine? It's not that, not at all. The question always and only is, can the single element replace its counterpart? Bromine is a halogen, a nonmetal, so it's going to try to replace chlorine, not magnesium. So I have to ask the question, can bromine replace chlorine? So when I look at my activity series, I want to find those on there. They're not listed because these are metals. So I need a little bit more complete. I call the larger one the NBA and the smaller one here the WNBA. There's fewer teams. Now, and those two teams don't compete. And of course, we know why, because the men's team and the NBA are frightened they would lose to the WNBA teams. I at least think that's why they don't play. Anyway, can bromine replace chlorine? And because bromine's lower down, the answer is no, it cannot. So you could try to write a reaction like MgBr2 plus Cl2, but you're wasting your time. It's not going to happen. So don't even do that. Just write no reaction. All right. The general form of a single replacement reaction is as follows. An element A plus a compound BC goes to a compound AC and an element B. Let's see here. Somehow I got a little bit lost on where we're at here, so let me go back up. All right, so we got our single replacement reaction done. And notice that it says here, that little A up here for single replacement says remember to use the activity series to make those predictions. So this is the activity series. There's one for the metals, and there's one for the nonmetals, specifically the halogens. And so I put a little graphic here, foiled again. Aluminum loses to calcium. See, aluminum's up here, calcium's up here. So calcium can knock out aluminum every time it will win. Well, if you have a single replacement, you must also have a double replacement. And a double replacement looks like this. It's a compound and a compound turning into two more compounds. So basically, it's like wife swap, where if it's wife and husband, the two wives switch places. So A and C switch locations. So A ends up with D and C ends up with B. Notice that it's CB, not BC, because you always put the cation first, the anion second. Now, with a double replacement reaction, it's kind of like junior high dating, where two people are dating first hour, they break up second hour, they're back together at lunch, and by the end of the day, they're dating another person. Well, double replacement only goes one way. And there's something called a driving force that will determine which way it goes. The only way a double replacement reaction will occur is if one of these two products is literally water, H2O. If you produce water, the reaction will occur. Or if one of those two products is a gas, the reaction will occur. Or if one of those two reactions is a solid, that's what the word precipitate means, the reaction will occur. And it is only those three driving forces, formation of a water, a gas, or a solid, that the reaction will occur. Well, let's try to classify some single and double replacement reactions before we go on. So we'll go back to our sheet here we were looking at. Now, let's look at number 5. When I look at number 5, I see an element in a compound forming an element in a compound. So that's A plus BC goes to AC plus B. That is a single replacement reaction. Let's look at the next one, number 6. Can you see a compound and an element forming an element and a compound? So basically, we have here AB plus C goes to, then we'd say, well, A gets kicked out, plus, then we're left with CB. It's still an element in a compound forming an element in a compound. So that is still a single replacement reaction. Let's go to the next page. Can you find one on this page that is a double replacement reaction? Look at number 10. Look at number 10. You have a compound and a compound forming a compound and a compound. So what's really happening here is, if we look at this carefully, is the lead and the hydrogen are switching places. And we end up with lead combining with sulfur, lead sulfide, and hydrogen combining with nitrate, nitric acid, HNO3. So this is an example of a double replacement reaction. Okay? And it turns out that lead sulfide, we're going to learn, is insoluble, forms a solid. We'll talk more about that on a different day. Well, let me go back to our reaction classes again. So we've hit all the big ones: synthesis, decomposition, single, and double replacement. Those are the ones that we'll need to know for right now. I'm going to mention a couple other ones just to kind of complete the picture for you. A neutralization reaction is always an acid and a base, and it forms salt plus water. So an acid, we're going to learn, is anything that gives a proton, an H+. A base donates a hydroxide, so that's our base. And then a metal-nonmetal combination is a salt, and water is the other product of a neutralization reaction. Now, technically, that is nothing more than a double replacement reaction, with water being the driving force. But oftentimes it's categorized as its own class. Acid plus base making salt plus water is called neutralization. And the last type I want to mention is combustion of a hydrocarbon. Anytime you burn something, it requires oxygen. So if I burn a hydrocarbon, something that contains carbon and hydrogen in oxygen, complete combustion will always produce carbon dioxide and water. Those would be the main types of reactions. If we really wanted to, we could throw in polymerization. Think of a polymer or a plastic type material where a polymer is made from many monomers. So polystyrene or styrofoam is made from the monomers of styrene, or proteins are made from the amino acids are the monomers, or complex sugars like sucrose are made from monosaccharides, right? Two monosaccharides combine to make a disaccharide, and so on. So I think you've heard of polymerization. I'm not real concerned at this point about the last three. We're going to be classifying the first four: synthesis, decomposition, single, and double replacement reactions. So they're all listed for you here, and generically what you're looking for in each one of these, okay? Remember, single replacement, we're going to use the activity series. Double replacement, we're looking for the driving forces. That means one of the products must be water or gas or solid. You can have more than one, but if they're both products soluble or aqueous, that means they dissolve in water, there is no reaction. We'll go ahead and add neutralization to that list. Acid plus base makes salt plus water, and combustion of a hydrocarbon producing carbon dioxide and water, and polymerization, just to kind of complete that list. All right, that's as much as I wanted to try to throw at you today in terms of classifying reactions. What I'd like you to do is try to, you've already balanced all these reactions, go ahead and classify them, right? So there's 36 of those for you to do. That will be really good practice, and then we'll check answers to see how you've done later. All right, thanks for keeping up, and I hope you're enjoying chemistry. Bye-bye.